Hello everyone, and welcome to our last video for the first section of our chapter over polynomials. Today we're going to start looking at the parent functions and graphs of some of our polynomials, and then graphing some more of them for ourselves. So we should be familiar with at least these first two. The parent function for a linear function is just y equals x. So that's our first degree function, and it goes through the origin and rises with a slope of 1, just a line. Our quadratic is a parabola, and the parent function is y equals x squared. It also goes through the origin, and it goes up in both directions in that kind of U shape. And then our cubic is y equals x to the third. This one's a little bit of a new one, so I'll graph it for you, let you see it here. So on my Desmos calculator, you can type in y equals x to the third or just x to the third. So I'll type in x to the third power. You can see it goes through the origin like all the other parent functions have. To the right, it goes up. To the left, it goes down. So one of the key features of graphs that we're going to be looking at today is called end behavior, and that is the direction, either up or down, the graph travels to the far left and the far right. So if you look up here, our linear function to the left is going down, to the right is going up. For a quadratic, it's going up in both directions. And for a cubic, again, down to the left, up to the right. And these are for the parent functions. We can do transformations to change those, but that is the type of end behavior that we're talking about. If you get pretty proficient with understanding the way that these polynomial equations work, you can determine the end behavior just by looking at the leading term when it's in standard form. So if n is even, that's the degree. So if we're talking about the leading term of a times x to the n power, it means we're looking for an even power like x squared. And then if a is positive, like our parent function is, the end behavior is up and up because it's going up at the far left and the far right of the graph. If a is negative, that were to reflect our graph upside down. So that would look like negative x squared. So now it reflects our graph upside down and our end behavior is down, down. And that's true for any even degreed leading coefficient. If the leading term is positive, we're going to be going up in both directions. If it's negative, we're going to be going down in both directions. Now, when the exponent is an odd number, whether that be a linear or a cubic, or if we keep going into higher odd numbers like the quintics to the fifth power, those go in opposite directions. So again, if a is positive, we go down to the left and up to the right. If a is negative, so let's look at like negative 2x to the fifth power. See, now that reflects us again. So instead of going down to the left and up to the right, we're going up to the left and down to the right. So if you get good enough at understanding our equations, you could just figure out by looking at it. So here's our fourth example. State the end behavior. So if we're looking at y equals 4x cubed minus 3x, the leading coefficient is 4, which is positive. And the degree is 3 because we go to the third power, which is odd. So keep in mind that odd degreed polynomials have end behavior that go in opposite directions. And when it's positive, you go down to the left and up to the right. So our end behavior should be down and up. And if you want, you can refer back to this table to double check. So we know a, our leading coefficient, is positive And in our degree is odd. So positive and odd is down and up. And I'll graph it just to show that as well. So let's say 4x to the third power minus 3x. So this looks a little bit different from the parent function of our cubic, but we're still going down to the left and up to the right. There is some different stuff happening in the middle that we're about to talk about, but the end behavior at the very far left is going down, and at the very far right is going up. The next thing I want to spend a little time on today is talking about a turning point. Our turning points are points on the graph of a polynomial where it changes direction. These can be either relative minimums or maximums on the graph. So if we look at a quadratic, all quadratics have essentially the same shape. They're all called parabolas. They're just a U shape. They can be transformed to be thinner or wider or open up or open down, but otherwise they do essentially all look the same. So we could have a minimum right here. That is a turning point on a quadratic because we are going down. And then at this point, at that minimum, we begin to start to come back up. And then on the other hand, we could reflect it, and it could be going up until it gets to this maximum and then start coming down. So all quadratics have exactly one turning point. Minimum, maximum there. Cubics are a little bit different. We could have something that looks like the parent function here, and that actually has no turning points. So there are some cubic functions that have 0 turning points. This is not a turning point here. It kind of changes the way it is moving, but it is still traveling up at all times. So that is not a turning point. There are some cubics that look a little bit more like this, which is kind of what we saw in example 4, where we've got a relative minimum here. I call that a relative minimum because that's not the lowest the graph ever gets. It's actually lower out over here. But in this little area, we do have a minimum relatively right there. Then we come back up, we have a relative maximum, and then we go back down. So it's possible to have 0 or 2 turning points on a cubic function. And then quartics, some quartics just look like parabolas, like the parent function there. Others can get a little funkier. So we're going up, relative maximum, come back down, relative minimum, come back up, maximum, come down. So this quartic has 1 turning point, and this one has 3. The higher the degree of the polynomial, the more potential turning points you have. And if it's an even polynomial, even degree of the leading coefficient, it's always going to be an odd number of turning points, either 1 or 3, or then if we get bigger, it could be 1, 3, or 5, 1, 3, or 7. Whereas cubics and all odd degreed polynomials have an even number. So all cubics could have 0, all odd degreed polynomials could have no turning points. Once you get past cubics or more, they could have 2. Quintics could eventually have 4. You get higher, you could eventually have 6. But that's identifying turning points. And then I'm going to just use this for one last example to end this section. Let's use what we've learned so far to sketch this graph. And I'm going to show you can absolutely use Desmos as part of this. So I'm going to graph -2 x to the 4th plus 8x to the 3rd minus 8x squared plus 2. I'm going to zoom in a little bit. And these are the things that I'm going to look for on this graph. First, let's find the zeros. We've talked about that in chapter 4. Those are our x-intercepts, the values of x that give us a 0 for the function. So one of them occurs at about negative 0.414, according to Desmos. One of them occurs exactly at 1, and one of them occurs at about 2.414. Then we're going to look for the turning points. So this is where our graph changes direction. So the very left, we're coming up, and then we get to a relative maximum right here. One of them is at 0, 2. That needs to be written as an ordered pair, and it's a relative maximum. One of them occurs here because we're going down, and then we start to come back up. So that is at 1, 0, and that's a relative minimum. And then the last one is right here at 2, 2, as we go up and start to come back down again, and that's another relative maximum. And then my end behavior, this is an even degreed polynomial, so it's either going up and up or down and down. And since this has been reflected with a negative leading coefficient there, that negative 2, means my end behavior is down and down. Down to the far left and down to the far right. So now I'm going to put my Desmos calculator away, and we can use this information to sketch the graph. So we have a 0 at about negative 0.414. So that's almost negative 1/2, not quite there. We have a 0 at exactly 1, and a 0 at 2.414 thereabouts. So a little less than 2.5. So all of those are points on my graph. Next, I can fill in my turning points. I know I have a relative maximum at 0, 2, a relative minimum at 1, 0. We'll just keep in mind that that's a minimum for later. And a relative maximum at 2, 2. And then finally, my end behavior is down, down. So I know that it should be going down to the far left and down to the far right. And then I'm just going to fill in the middle. So this was a relative maximum, so then I come down. This was a relative minimum, so I'm going to come back up. That was a relative maximum, so that's where I'm going to start to go back down again. And that is how we can use some of our key features of a graph to sketch the graph.